This is ELN 232, Introduction to Microprocessors. And before we start with the arithmetic instruction set this week, I wanted to review 2's complement arithmetic. Now, understand that the microprocessor cannot subtract values. It can only complement values and add values. But the microprocessor can accomplish subtraction through adding the 2's complement of the subtrahend to the minuend. Now, the 2's complement is the 1's complement plus 1. And the 2's complement of a binary value is equal to that binary value multiplied times -1. Now, in ELN 133, you learn that to change or to find the 1's complement of a binary value, you simply change the zeros to 1's and the 1's to 0. For example, the 1's complement of 0010, 1000 is 1101, 0111. But the 1's complement is really the binary value that you obtain when you subtract a binary value from 1. For example, the 1's complement of 0010, 1000 is obtained by subtracting that binary value from 1111, 1111. So you see, regardless of the method, the 1's complement is the same value. Now, the 2's complement is the 1's complement plus 1. So the 2's complement of 0010, 1000 is the 1's complement plus 1. So here is the 1's complement, and we add 1 to obtain the 2's complement. Now, in ELN 133, you undoubtedly learned a shortcut method of determining the 2's complement of a binary value, and that is that you start at the right up to and including the first 1, you leave the bits unchanged. Continuing on to the left, you change the 0's to 1's, the 1's to 0's. So it doesn't matter whether we take the 1's complement and add 1 or use this shortcut method, we obtain the same value for the 2's complement of a binary value. Now let's review our rules for binary subtraction. 0 minus 0 is 0. 1 minus 0 is 1. 1 minus 1 is 0. And 0 minus 1 is 1. And we borrow 1 from the next more significant column. Let's look at a binary subtraction operation. For example, let's take 0, 1, 0, 0, 1, 0, 0, 0, and subtract from it 0, 0, 1, 0, 1, 0, 0, 0, 0 minus 0 is 0, 0 minus 0 is 0, 0 minus 0 is 0, 1 minus 1 is 0, 0 minus 0 is 0, 0 minus 1, we have to borrow 1 from this column, which makes this column equal 1, 0, and 1 from 1, 0 is 1, 0 from 0 is 0, 0 from 0 is 0. Now, I want to go back and talk about subtraction for just a minute. I feel confident that most of you have forgotten this from third grade math. But when we perform a subtraction operation, the number we subtract from is called the minuend. M-I-N-U-E-N-D. The number we subtract from the minuend is the subtrahend. And of course, the result is called the difference. Now, subtraction can also be accomplished through 2's complement addition. If I take the minuend 0, 1, 0, 0, 1, 0, 0, 0 and add to it the 2's complement of the subtrahend, note that the result of the subtraction is the same. Now, when performing this addition operation, note that there's a carry out of the 8-bit group of 1. But that carry out simply shows us or means that the result of the subtraction operation is a positive number. Let's look at an example when we end up with a negative result. In this case, we're going to subtract 0, 1, 0, 0, 1, 0, 0, 0 from 0, 0, 1, 0, 1, 0, 0, 0. Now, when we subtract a larger number from a smaller number, what we do is simply reverse the subtrahend and minuend, perform the subtraction, and put a negative sign in front of the result. But this subtraction above is accomplished through 2's complement arithmetic by adding the 2's complement of the subtrahend to the minuend, giving us a result or a result of 1, 1, 1, 0, 0, 0, 0, 0. And note that the carry out of the 8-bit group is a 0. This carry out of 0 tells us that the result is negative. And this result will be in 2's complement form. The 2's complement of 1, 1, 1, 0, 0, 0, 0, 0 is 0, 0, 1, 0, 0, 0, 0. So regardless of whether we perform this subtraction through brute force, as shown here, or through 2's complement addition, shown here, the result is the same. Now, the problem with the methods we've just looked at is that in the computer or dealing with the microprocessor, we're typically going to express all of our values in hexadecimal. And we need to have a method to perform subtraction operations on hexadecimal values without converting them to binary. And we can do this through what I call 16's complement addition. Now, if I subtract a 4-bit hex value from F, we get the 15's complement. The same idea that when I subtract a bit from 1, I get the 1's complement. If I subtract a hex value from 4 ones or F, I end up with the 15's complement. And if I add 1 to the 15's complement, I get the 16's complement. So the 15's complement of 2, 8 in hex is D7. The 16's complement of 2, 8 is D8. So what this means is that D8 equals negative 2/8. Let's look at some hexadecimal subtraction. For example, 4/8 in hex minus 2/8 in hex gives us 2/0 in hex. Let's see if I can accomplish this subtraction operation through 16's complement addition. So we take the minuend, 4/8, add to it the 16's complement of the subtrahend, and we end up with a result of 2/0. Again, I have a carry out of the 8-bit group of 1, but that carry out simply shows us or tells us that the result is a positive number. Well, what happens if I subtract hex values and get a negative result? Again, typically when we subtract a larger quantity from a smaller quantity, we simply reverse the position of the minuend and subtrahend, perform the subtraction, and then stick a negative sign in front of it. But this subtraction above would be the same as taking 2/8 and adding the 16's complement of the subtrahend, or B8. And the result of this addition operation gives us E0, and there's a carry out of the 8-bit group of 0. And this carry out of 0 tells us that the result is negative, and it is in 2's complement form. If we find the 2's complement of E0, we find that it's 2/0. So performing this operation using 2's complement addition, or if you wish, 16's complement addition, we end up with the same result. Now, a few years ago, I was doing a lecture on this to one of the classes, microprocessor classes, and I got to thinking, gosh, if this works for 2's complement, binary values, if it works in 16's complement for hexadecimal values, shouldn't it work for decimal values? So I sat down and did some ciphering, and I came up with definitions for the 9's complement and 10's complement of decimal numbers. So if I subtract a bit from 1, I get the 1's complement. If I subtract a byte from F, I get the 15's complement. So if I subtract a decimal number from 9, I should end up with the 9's complement. The 9's complement of 45 is 54. And just like the 2's complement is the 1's complement plus 1, the 16's complement is the 15's complement plus 1, the 10's complement of 45 is 55. Let's see if it works. So let's take a decimal subtraction operation. 67 minus 45 gives us 22. Can we obtain this result through 10's complement addition? Well, let's take 67 and add 55, the 10's complement of 45, and note we get the same result, 22. And we have a carry out of the 100 or the tens column of 1, but that carry out simply tells us that the result is positive. What happens if we do a decimal subtraction operation and obtain a negative result? For example, 45 minus 67 gives us negative 22. So that subtraction operation would be the same as adding the tens complement of 67, or 33, to the number 45, giving us a result of 78. But note that the carry out of the tens column is 0. That tells us the result is negative and it's in tens complement form. If we find the tens complement of 78, we find that it is 22. So we can obtain or accomplish subtraction of binary values using the 2's complement. We can obtain we can perform or accomplish subtraction with hexadecimal values using the 16's complement. We can obtain or perform subtraction on decimal numbers using the tens complement. And we didn't look at the example, but we can subtract octal values using the 8's complement.